Well, welcome back, folks. We just have a few seconds to go. And we're there. And this is kind of an exciting week. We're now on week 12. So once we complete this week, that's the 75% mark. So congratulations, folks. We're getting through it pretty quickly at this point. Other exciting thing on the announcements list is this chapter 15 is the last chapter of the entire semester. So once we complete this, we've done all the course content that we set out to do. So we're nearly there in that perspective as well. But chapter 15 is long, so it kind of counterbalances that comment. Chapter 14 is a little bit shorter, but we're going to spend some time there, make sure we really understand those examples. We have three big ones that we're going to go through to get a feel for how confidence intervals go when it's quantitative data. There's a lot to discuss with how does it work, what is working underneath the machinery. But when it comes to actually doing the interval, y bar plus or minus t star standard error y bar, it's going to feel a lot like exactly what we did in chapter 13. We're just switching over from the statistic to a p-hat statistic, the sample's proportion of successes, and a different standard error, a different z-star, which is effectively for us a table lookup. So to get really good practice on this method right here, quiz number 9 will be your guide on that. So quiz number 9 is going to be the next really big quiz that's going to help out on the third exam. And I cut the third exam kind of short on the content. I felt like 2 confidence interval procedures is a lot on one exam, especially when we're just barely getting through chapter 14 material. So that's why when I wrote out the exam 3 material last week at the end, I capped it off at the chapter 13. So chapter 7, this one I believe is on quiz number 8. Let me think about that. Chapter 7, I believe, is quiz 7. Chapter 10 is based on the quiz 8 that came due last week. And quiz number 9, the one that's posted, is going to be chapter 13. That means the quiz 10 that's posted here, this one's not going to be relative to the exam 3 information. It's going to be a chapter 14 kind of quiz, only because, again, we cut this one short for this exam, ending on chapter 13. So we'll be doing the standard thing. I'll remind everyone when we're back on Wednesday. On Thursday, the standard thing would be we'll call for questions on exam 3 and spend as much time as we need to taking student questions. But that's where we're at so far, folks, and that's where we're going at the moment. Any questions so far before we get started? Okay, well, let's dive back in, not exactly where we left off. We're on example 3, not 5. Sorry about that typo there. We're about to do the confidence interval procedure, y bar plus or minus t star standard error. But the thing that makes this also very tricky to really nail down conceptually is the central limit theorem. This thing is kind of a tough statement to really think about. It was tough in chapter 13. And I think it's trickier in chapter 14. The ordering of the textbook is kind of logical once you see both of these central limit theorems. The central limit theorem says you have a sum population. You're measuring a quantitative variable, so the parameters are naturally mu for the population's mean, sigma for the population standard deviation. The picture is if you repeatedly sample at the same size n from this population and calculate these 2 statistics, place into the histogram y bar, and you get a normal distribution. So this is what the central limit theorem is saying. The next parts tell us of the central limit theorem, tell us the center is mu, which makes sense. It means all of these estimates are estimating the right thing in the very first place, the unknown population mean mu. It also gives us a standard deviation, sigma divided by the square root of n, and that's what led us into the t distribution, the fact that there are 2 parameters at the same exact time we have to estimate, more tricky than chapter 13. But the trickiest thing about this all is the comment in purple. The central limit theorem tells us if the population is normally distributed, or if it's even just close to normally distributed, if it's very symmetric, if it's unimodal, your sampling distribution y bar is either exactly normal or very, very close to normal. Rule 4 is where the central limit theorem actually shines. If we were constricted to only populations that are distributed normally or very close to normally distributed, this theorem is not as much value as you'd think it'd be because there are plenty of populations we care about that are significantly skewed, and we saw them in chapter 2. So rule 4 says, if your sample size is large enough, that's a hard question to answer, but if it's large enough, then no matter what the population is, y bar is well approximated by the normal distribution, or said this way, by a normal curve. So that's the big statement. That's what's being said here in purple. And that's one thing that we're going to take a look at too one more time for a simulation, just to kind of get a warm up on what is a sampling distribution and what is the central limit theorem over here trying to say. We didn't do this last time because I felt like doing too much at once is kind of hard to put in your head. So after sleeping on it for a few days, we're going to take another look into essentially what this picture is all about. Well, any questions or comments at all, folks, before we give this a try? Okay, this is similar to what we did in chapter 13. The TID4 Plus is great, but the technology is just not good enough for this scenario. So we're going to use a slightly different calculator. I forget, it logs you out. It's too smart for its own good. So this is the R calculator with a program called RStudio on top. I mentioned before, if you're going to take a law of statistics, the next statistics class might be Math 3350 Statistical Methods. This is probably software that your course is almost guaranteed to be using. And we have a small mental break while that loads. Okay, so we're at the start of this. So what I'm going to be doing is producing a histogram over here, kind of like what we did in chapter 13. But I want to focus first on just the population itself. So I have something kind of like a normal distribution, except that this one is really, really skewed. This is the chi-square distribution, something that comes up in statistics. If you'd say, looked at categorical data with 3 outcomes or more, that would be a chi-square distribution working in the background. So if we set the degrees of freedom to 1, this is going to control how skewed the population is. I'm going to take a sample size of 1,000 and place the histogram of those 1,000 observations. So the R statement there just says we're pulling a random sample. Chi-squared is just a highly skewed distribution. That's a mathematical thing we can sample from. At sample size n, with that skewness factor, degrees of freedom. So here's what it looks like. And this is just the first random sample. It's a very right skewed distribution. It's a sample size of 1,000 observations, all drawn randomly, giving us that distribution. So that could be our population we're discussing here in the central limit theorem. If this is something that's really important for us to study, even though it's highly skewed to the right, if our sample size is large enough, we can still use the central limit theorem. So sample another different 1,000 observations and it looks slightly different. And every time you sample a size 1,000, notice it changes. That's just the sampling variability that we see when we select a random sample. And now what we're going to do is imagine what would happen if we took the average of all this data. That's going to be what this part is all about. The random samples themselves. We can calculate the sample mean, the sample standard deviation for these data, just record the number, do this over and over and over again, and start collecting values into a histogram. So this is the underlying population. Now we're going to move to the next layer of abstraction, taking over and over again repeated random samples and computing the statistics. Any questions first with the underlying population? Okay, well, maybe one last thought. I said that the smaller the value of df, degrees of freedom, the more the skew. So let's take a look into that one more thing before we move over. We go from degrees of freedom 1 to degrees of freedom 0.1. Here's the new graph. This one has almost all of the observations between 0 and 0.5. Run it again. Kind of the same picture. There's almost nothing here. In fact, the sample is so large that the heights here are so small, you can't even see the data, but it wouldn't have plotted this far if there wasn't any data. Drop this to 0.001. And the skew is even worse. It looks like all of the observations are basically between these values. Nothing is showing up here whatsoever. So in this way, the smaller the value of the degrees of freedom, it's as if everything is here at the very start, and then you just get loads of what looks like outliers off to the far right at this point. So imagine that's our population. We'll bring it back to 1, start with something that's pretty skewed, but not that crazy, and then we'll make it to more and more skewed as we investigate this. So here's where it looks kind of crazy, but from this part right here, the population, this is all we're doing right here, is grabbing the population. The next part, we're going to grab a sample size, take a random sample, and that's all this is doing. Grabbing a sample size, taking a random sample, and putting it into histogram. Sample size 1 is kind of strange, so let's start small. Let's suppose we had a study at sample size 5. This is something that could have been investigated by people if small sample sizes just make sense, like with the Gossett person we were discussing last class. So this blue box represents taking just 1 sample, calculating the mean, and just collecting the result into, I called it X bars. Sorry about that. Think of that as a Y bars. Then this part is meant to mirror this part right here. I said this in a weird way. This part, where we take more and more random samples, is what this portion is doing over here. Repeat. That says 10,000 different times, 10 to the power 4. So here's the repeating factor. Calculate the mean every single time we repeat the sample. Do it over and over again. And then the very bottom is just going to put all of it into a histogram. So these are the 3 different elements we see here in the central limit theorem graphic. And that's what this calculator is going to do. Okay, so let's run this. We're placing all of these histograms, or excuse me, all these sample means into a histogram. And here's what we get. It's not the best picture, and I have superimposed on top of it a normal curve, the best fitting one that would match the situation, the one with the right mean, the right standard deviation. But notice it does not fit this picture. This graph is still skewed to the far right. And really the only thing that can save this is bumping up the sample size. That's what this part of the central limit theorem was all about. It said, if your sample size is large, then the central limit theorem becomes effective. Our sample size was small, just 5 observations is not a lot for highly skewed data. And this is the really rough rule of thumb. If your sample size is greater than or equal to 30, then in most situations, the central limit theorem is probably effective. It would take something that's extremely skewed, a little bit unusual, for this rule of thumb to break, but those things can be encountered in practice. So if we bump the sample size up high enough, we're going to see a picture that looks like this. Our curve should fit on the data. So first thing we can do is just triple the sample size, go from a sample size of 5 to 15. Now it's the same sample size in all of these studies. And remember, we have 10,000 of them we're considering in this simulation. So repeat this. And that's not bad. It's not perfect, but there's still some skew to the right. The peak of the curve doesn't seem to match perfectly the peak of the data, but it's pretty close this time. If we double it and get it to the rule of thumb, sample size 30, here's the picture we get. Still not perfect, but this is pretty accurate at this stage. The right skew will never go away completely. The peak isn't perfectly set the way we'd like. We'd like to drag it to the left if we could a little bit more. But sample size 30 is going to give us a pretty rough and crude approximation. For a population that's highly skewed, that's kind of fantastic. It says we didn't need too huge of a sample. We take another 10,000 different samples and run this again. Here's what it looks like that time, slightly different. Do it again. Might be the best picture so far. But the thing that only makes it really a better picture overall is bump the sample size even higher. Go from 30 to 300. Here's what you have this time. This picture is almost exactly this graph right here. The central limit theorem didn't care how skewed the underlying population was. We can control the skewness and make it worse and worse. But the central limit theorem is all about this statement rule 4. If the sample size is large enough, the normal curve pops out. So that's seeing it as a simulation. That's a lot to think about. Does that help make sense a little bit more of what's going on with the central limit theorem? Or does it still feel kind of crazy in a way? Well, to think about it a little bit more, let's imagine it's more skewed. Like we were investigating over here, the smaller the number for degrees of freedom, the higher the skew. So if we want more left skew in the data at 0.1, this is what the population is going to look like. So highly left skewed. If we take 10,000 observations at sample size 300, here's what we get. Still, it's doing a great job. Even for that highly skewed data, here it is on the left, at sample size 300, which is a pretty large sample, central limit theorem is not perfect any longer. Some right skew is appearing, but it's highly effective. Make it even more skewed. The smaller the number here, the higher the skew. And now it's breaking down even further. But the idea with the central limit theorem, what makes it a really kind of freaky fact about statistics is it didn't actually matter how skewed it is. It's a sample size that matters that makes a central limit theorem work. Bump this to a sample size of 3,000. It's going to take the calculator a while, but we're back to that nice picture. And we could play this game forever, make it even more skewed. It's okay through the central limit theorem. Just make n larger to overcome the skew that you see in your sample, and we'll be in business. So checking these kind of conditions is really kind of tough because you need this histogram of the sample to determine, is the skew too much or is it our sample size going to be effective? So we're not going to check the conditions as closely as we could in chapter 13. But if you wanted a really crude rule of thumb, that's what this is. With the emphasis, it's a pretty blunt one. And for it to be effective, you still have to plot your underlying population like we were doing over here just to see how skewed is it really. If you're seeing level of skewness like this, nothing supremely crazy. It's hard to find data that's worse than this for real world data. Then sample size at 30, we found it was pretty effective overall. So that's the end of this calculator simulation thing. We won't open R again for the rest of the semester, but it's interesting to see some of the biggest ideas you can see in statistics can be just explored using this kind of stuff. The more statistics you take, the more you use these weird tools. And it makes sense because for the TID4, if you had a sample of size 300, nobody wants to go to stat edit and put those in one by one. That would be a nightmare. So you're either using Excel, but even Excel breaks down. There's a limit to how much data you can put into Excel. So you start to use other tools like R or RStudio that can handle gigantic sample sizes. Well, that was our refresher on the central limit theorem. Any questions at all, folks? Either as the statement here or as the graph here? Okay, well, the short of it is the central limit theorem tells us the normal distributions are something natural that come up in the strangest of contexts. But the second problem we discussed last Thursday, we did a lot on Thursday, was the fact that this is a two-parameter family for a distribution means estimating mu is not good enough. We also had to estimate sigma at the same exact time. That means we went from a normal distribution to a related one, the student's t distribution. We explored some concepts relating to this. The t distribution, like the normal distribution, is completely symmetric. It's heavy-tailed. As the sample sizes get larger and larger, they become closer and closer. However, the purpose of using the t distribution is because of that standard error right there. S estimated the population standard deviation sigma. The whole interval here is estimating the population mean mu. So we have estimates on estimates when we use that standard error. Using T star is what allows us to incorporate the fact that's a second level of estimate we made. It has its own margin of error. It's all encapsulated inside T star itself. So this is our brand new interval we were working with. It's indexed by the degrees of freedom, and example 2 is just calculating a couple of these. Thanks goes out to Coral to spotting one of the mistakes made in last class on Thursday. On Thursday, this was a mistake right here. When I first put the degrees of freedom in the calculator, I made a mistake and actually wrote 190. That's a simple mistake, right? Because we're looking at a sample size, but 189 really has to go there. And you can imagine if the sample size was 19 and I put in 19 again, the critical values would have been very far off, not just in this fourth decimal place where the correction was made, it would have been quite a bit off. MyLab statistics might mark this wrong if the standard error is big enough, but if we made a mistake on a smaller sample, it's almost definite we would miss the question. So the big reminder is, don't forget to put DF here. DF for degrees of freedom, not the sample size. Really, this is the only major thing that's new in chapter 14. We're calculating the degrees of freedom every time for each new problem. If the confidence changed from 99% to 90%, you still have to redo it, even though the degrees of freedom are the same. We get a different critical value. The sample size changes, a different critical value again. But aside from that, it's a very familiar object. For emphasis, here's the doodles that we had at this note. Here is the doodles we had at the start of class. There's really, really nice parallelism where we go from p hat to y bar, plus or minus a critical number, happens to be t star this time, and then just a brand new standard error from p hat to y bar. So we're doing this formula next, and this takes us to the actual example 3 we're about to do. Any last questions with any of the information so far? Central limit theorems, t distributions, or critical numbers? Okay, so all this.
Both of those, right?
Sorry, say again.
Both of the ones from above.
In these notes for chapter 14, or
standard error.
Oh, hang on. Let me go back. Oh, gotcha. So for this chapter 14, it'd be just this standard error right here.
We haven't done it.
Exactly. So this is the new one we're about to try. Yeah.
That one with and that one. Or do you consider that all one formula?
This is all one formula right
We're
here.
going down.
This right here?
That with the T star one.
Yeah, so this is one formula, and this on the right is just saying how to compute the standard error y bar part.
Right.
Yeah.
But we're gonna do both of that right now.
Exactly. Yeah.
Okay.
Exactly.
I didn't miss him.
Not at all. You're in good shape.
Okay.
It's a lot of stuff going on in chapter 14, so I understand the feeling for sure.
Right.
Yeah. Well, this is kind of like the nice part of chapter 14. Everything we've been doing so far is how does it work and why does it work? And this is the actual mechanics behind it, the stuff that we'll write down, the conclusions we'll make. And it starts off just like any other statistics problem, something that we could have looked into way back in chapter 1. This could have been a problem discussing statistics versus parameter, population versus sample. It starts off, looks like this one is about crime statistics. The Federal Bureau of Investigation compiles data on robbery and property crimes, publishes the information in, you can freely look this up, population at risk, rates, and selected crime indicators. A lot of the context was taken out of this so that we can just focus on the actual information. But this is a great source of statistics problems if you ever want to just look into a random set of data. It says a simple random sample of 25 pickpocket offenses. Well, that already gave us a sample size, so we should write that down to start us off. So 25 randomly selected pickpocket offenses in a particular area yielded a sample mean loss of $513.32. But because they said sample mean, that's the next element we need. They gave us the y bar value. These are things that we have to pick out in context as we read them. So it's always a good idea to read this a couple times, make sure we didn't miss anything. Y bar is 513.32. Notice this isn't about successes or failures any longer. There's no percentages, there's no proportions. This time we're dealing with fully quantitative data, so that's why we're using the new method. There's also a sample standard deviation loss of 262.23. So that's our other statistic, S. S is 262.23. So this gets us started. Now, next thing we're going to estimate is the unknown parameter, but just to tie together some concepts, or yeah, concepts is the word I was thinking of. This is quantitative data. So any quantitative data that we have in this kind of situation indicates right away parameter is mu. But if the parameter is mu, it tells us the confidence interval procedure will be that whole y bar plus or minus t star times standard error y bar. I mean, we know in chapter 14 that we're estimating the parameter mu, it says so. We know that this is the formula, it says so in the notes. But if this was a random final exam question, these are the thoughts and connections you want to make. Quantitative with the parameter mu with that specific procedure. And you know, that's a pretty quick line that you could put in your notes and you have the entire confidence interval procedure ready to go. So next, it's the unknown parameter we're gonna write down.
On an exam,
Yeah,
if I remember right, we have a way of figuring out the standard deviation, right?
yeah. So that's what's gonna happen on, like, say, this problem right here. So we'll have to crank it out ourselves by going stat edit and dumping in the data.
Okay.
But for some problems, just depends on the problem on the final exam. It could be this one. If I try to make the exam shorter, I'd probably go for something like this. If my exam can fit this one, maybe I took out another question to make it fit, I might give a problem like this one. So now we're doing kind of like chapter 2 and chapter 14 all at once, finding the summary statistics here. And also for the homework and MyLab statistics, there's kind of a mixture of both as well. You might have to crank them out by hand for some of the problems, but not all of them. Other questions so far? Okay. Well, it says the unknown parameter, but once we spot quantitative data, we'll write it out like this. This one's tricky too, just like it was in chapter 13. So let's write out kind of a schematic, just like we did in chapter 13, that you could use in virtually any kind of situation. The format or the schematic, the fill in the blank for mu as a parameter would look like this. It's going to be equal to the population mean, and then your first blank is going to be, well, in the last chapter it was describe what the successes are, right? But this time, if it's a quantitative variable, the first thing you'd say is mention the quantity for the quantitative variable. The blank didn't have to be that long, but my writing just turned out a little bit longer. So it's going to be the population mean of some quantity, and we have to say what it is to nail down the context. Then we would say for all, the all here is just another, again, kind of a buzzword to indicate we mentioned the population as well, just like in chapter 13. So for all, another blank, and this is the population. And again, this is basically what we did in chapter 13, except the only change here is we don't say successes and failures because we don't have that notion any longer. It's no longer categorical data. So we have to remind ourselves, what is the quantitative variable? Usually there's going to be a unit, and if you write your unit in when you write out the statistics, that kind of helps your brain connect the dots together. So it's going to be the mean. Well, what was the 513? That was a loss due to a pickpocket offense in this particular area. So we can say the population mean, amount lost, and that would do the job. You could say the amount lost in dollars to be really specific. But I would say that part could have been left off and it would have been just fine. To make sure we mention the population, let's read this again. If you know what the sample is, you can infer what the population had to be. It was a simple random sample of 25 pickpocket offenses in one particular area. The problem didn't say which area because we're not trying to single out anybody, but I bet you it was a really busy airport. Notice the amount lost is a chunk, a big set of cash, as if someone's stealing cell phones, iPads, tablets, that kind of stuff is what's being stolen, really. So this is probably an airport in some big city, probably a large international airport, something like that. But what we can say is it's a population mean amount lost in dollars for all pickpocket offenses in this area. We don't know exactly where, but it seems to be a pretty targeted spot. And as always, when it comes down to this parameter, you can be very hyper specific. There's a lot to think about here. There might be stuff that you feel like is missing or something or different take you have on this parameter. Anyone see anything that might just seem missing or something you'd want to include or a different take?
For the population.
Yeah. Does it feel like we nailed down the population 100% based on the context given? I would say this is full credit for an exam situation, by the way. But if you were really thinking on this, you might not be totally satisfied with this so far. Here's one way to think about it. When it says all pickpocket offenses in a particular area, that's something that exists, right? It happens, it's in history. But how do you figure that out? How do you know you have a sample size from that? These were crimes that were reported. That's how the FBI got these data. So these are people who reported the crime. I was pickpocketed. I lost X item valued at this dollar amount Y. But a lot of people sometimes get pickpocketed and they feel terrible. Maybe they fly off and they never even notice they got pickpocketed and they don't even know when it happened. Was it at the airport? Was it at my destination? Did it someone rob my house and I forgot to pack it? So these were just the ones that were actually reported by the FBI because someone filed a police report. So these are all pickpocket offenses in the area that were actually reported. The total of every single pickpocket offenses isn't likely where the random sample came from. And it's hard to know how you would even do that. You would have to be like super surveilling this area to make that happen and have some pretty crazy data. The FBI probably doesn't have that kind of budget whatsoever. So if you're being really specific on the population, that's a way to refine it just a little bit more. But the standard reminder is it's okay to make your context a little bit terse. If you didn't write that in, this would be a pretty great full credit response so far. But anything interesting you might see is something that's always interesting to discuss, to think about what are the limitations of this study. And it's kind of like an example that we mentioned before, I think back in chapter 13, where the sample were kids reporting having been drunk. That's another one that's different. Those were people self-reporting. The population probably wasn't necessarily all kids that had been drunk whatsoever. Same kind of problem on this one as well. But going with this parameter and with the understanding, this is just based off reported crimes because we're talking about the FBI's data set here, probably pulled from local police stations and such. We can at least go forward with the method. So here's where the funner part of the problem starts, the actual mathy portion. We need next a standard error, but first, any last questions or thoughts on part A? Okay, let's work through the standard error next. And hang on, I'm looking at my color coding. This is kind of nitpicky. I guess I didn't put anything specific here from here. Let's just keep this color coding consistent all the way through. So I'm going to use green for the mean, blue for the standard deviation. So for the standard error of the sample mean, symbol this time is SC Y bar, SC for standard error, White bar just because that's our new statistic this time. So this becomes kind of a fun standard error to calculate based off what we've done historically. Last chapter, this was a bigger operation. This is just S divided by square root of N. So this will be S262.23 divided by square root of the sample size N is 25. So just 5 down below there. I'll toss the whole thing into the calculator just for practice of what that would look like for a nastier number. So this goes in as 262.23 divide by, hit second and power 2 for the root as usual, and throw in 25. So that's our standard error. This is the approximate to the population's standard deviation, but this is another approximation on top of the first approximation, Y bar. But nonetheless, we've got a number. This would have the same unit as the data. So in dollars, 52.446. We didn't have to round on this one, so to 4 places didn't have a lot of meaning this time. From there, the next big thing is to come up with T star. And this is the one where we want to be a little bit more careful. This is the next thing that's new. First thing we can say is if the confidence is at 95%, we drop that in as a 0.95. And we will compute the degrees of freedom quite a lot. So it's good to have an overall procedure. And this is what it looks like. In the calculator, we next put in the area. As a formula, this is always 1 minus C divided by 2. But it has to go in as a decimal number. So that's the next thing. It'll look like this really, 1 minus 0.95 divided by 2 when you enter it into the calculator. So that's one thing we need. The next thing we need is the degrees of freedom. We abbreviate that to just DF, and its formula is nice, N minus 1. So substitute in 25 for N, reduce it by 1, and we have 24 degrees of freedom. So these are the 2 pieces of information we need. From this, we get out to T star. And just a reminder for the notes, we have to use inverse norm. So it's kind of fun using the next newer functions in the calculator. Hit second, and then the vars button. Go down to option 4, or just punch 4 for inverse norm. Area, looks like I already have just about the right structure. It has to go 1 minus new level of confidence, 0.95, then divide by 2. Then you'll essentially update degrees of freedom every single time. And make sure you pick this number. It's natural to want to put in the sample size, but it's 1 less, 24. And this problem would make a big difference. If I put in 25, and this was a MyLab statistics problem, I pretty much would bet that they would mark this one incorrect, which is highly frustrating. So at 24 degrees of freedom, and to 4 decimal places, here's our critical number. We pick out the positive value and write it as a 2 point, let me fix the pen, 2.0639 upon rounding. Aside from this part right here, all we're going to be doing next is just putting together this formula here. Well, any last questions at all, folks? Getting your T star out? Anyone get anything slightly different or any questions about it? Yeah, absolutely. So go second vars, inverse T. Let me just reset this just to make sure I didn't have anything weird carrying over. Oh, right. I'm not sure why I put that on there. Sorry about that. Let me correct the notes right here. I think that was an old habit. This should have been inverse T. I think a box around it will help me out at least. And I mean, that's a good one to compare with your other value. If you use inverse norm, you're getting about a 1.96. This one's guaranteeing a wider margin of error with this new value. So 1 minus 0.99 divide by 2 should give you that. Hang on, now I've got a weird number. Let me try again, second vars. Inverse T. I'm getting a weird number all of a sudden. Oh, I have a problem with my division. Let me try again. Second vars, the next thing that can go wrong in the calculator is picking the wrong function because the notes was incorrect. But, well, that prints out as one parentheses. When I hit enter on this, came out as 2. That's weird. Yeah, go ahead.
Yeah, you're doing a 99.
Oh, I see. I'm getting all mixed up on this. Let me try one more time. Inverse T, 1 minus point. Thanks for spotting that. 9.5 to match the confidence. 24 degrees of freedom. And we're back to that number there. Does that look better to folks so far? In the calculator, yeah. The reason for that is back to this picture over here. When I give it, say, the 1 minus 0.90 or 0.95 divided by 2, I'm putting the value in the left tail because this calculator here only calculates the left tail value. But whatever you have on the left tail here, it's symmetrically equal to the right value that you would want to use. So you just take off the negative sign. So on each time you do this, you can just take off the negative sign and have the right value. As far as it would go on, say, an exam question, really, whether you gave me a positive or negative doesn't matter at all because you use both the values, positive and negative, altogether. But if this was a MyLab problem, you have to give a positive value. So whatever you get in here, just take off the negative sign and you've got the right number. Other questions at the moment? Okay, so that was the next new thing. The rest of it is just put your statistics and information back together in the procedure. So let me take a quick screenshot of the statistics. For part D, when it says construct a 95% confidence interval, this is about where we'd be looking once I scroll to the right value here, right place. So just write down first the whole procedure. It's going to be y bar plus or minus t star times standard error of y bar. As well, use yellow for color coding. So that t star is going to plug in. And I have blue for standard error. Let me fix that real quick. This all together becomes 513.32. Add or subtract 2.0639. Multiply it by 52.446. At this stage, it should feel just like deja vu, doing almost exactly what we did in chapter 13, just substituting in those 3 different values. Now it's back to the calculator. This will imply, as immediate conclusion, that we have mu, the population mean, the parameter that we were estimating in the first place, constrained between 2 particular numbers. So part C is kind of the tricky part, but from here on out, it's just plugging it into the calculator. That whole line goes in as 513.32. Order is important. So you put this in MyLab statistics, you have to give the smaller number first. So let's do the minus first, just to keep in the right order. 2.0639 times 52.446. So this is the lower bound. And because this is money, we can round to the nearest cent, $405.08. Then standard trick is to copy that operation down. Go left here to flip the sign to plus. Oops. There we go. And here's the upper bound, $621.56. And at this stage, we're done. This is the entire confidence interval estimate. So the y bar value, y bar is 513.32. This estimated the parameter mu already. The population mean average loss is approximately $513.32. But when we add and subtract this number right here, we're saying more. We're saying what is the margin of error in making that estimate? And when we say at 95% confidence, what we mean is this procedure works, as in our value for mu is going to be between whatever two numbers we come up with 95% of the time. This has a 95% success rate altogether. One last concept that could come in as a MyLab statistics problem. It doesn't ask this a lot, but sometimes it does ask for the margin of error. It would be this part right here. So this is the margin of error in estimating mu with y bar, the sample mean. It's often written as a lowercase m, and its formula is t star times standard error of y bar. So you'd really just be multiplying these two things together to get your margin of error when it comes up. This is not a question that I ask a lot personally on a quiz or exam, but in some of the MyLab statistics questions, not a lot of them, this is a question that they do ask. So this is all they're really asking for. Let's take 2.0639 times 52.446. So the margin of estimate is $108.24. And just a reminder, this is again mostly for MyLab homework. Well, last thing we have to do is just give a practical interpretation for the confidence interval.
Run that, do that part again, so you do. Oh, you just do that one portion of.
Yeah, just this block right here. So it's always the part that you're adding and subtracting to the mean y bar itself to give your margin of error. The same concept in chapter 13, except it was a z star and standard error p hat. Other questions at the moment? Okay, well, we're nearly there, folks. This is, again, is the major part of the course. Getting the confidence interval is fun. It's like a math problem. You just have to follow the formulas in parts B, C, and D very carefully, particularly with getting the right confidence in the calculator, making sure to use inverse T. There are a lot of details. But once you get here, it's still not good enough, which is sort of frustrating. It's because we have to explain to everybody who reads our work, what does this interval even really mean at the first place? So we go back to the top. When we described the parameter and used the context, we were telling people what our conclusion was going to look like in the very first place. So copying this down, this is exactly similar to what we did in chapter 13. We go back down to the bottom here. We start off by mentioning the level of confidence that we have in our procedure, the one that we used. We used the 95% confidence level. So we'll say with 95% confidence. Next, we come down here to this level. We're just now at this stage trying to say, what are we estimating in the first place? So we rewrite again what mu was. We'll say with 95% confidence, the population mean amount lost, and I'm going to leave off the parts in dollars because we're going to mention the dollar sign, so that part will be clear. Because we're mentioning the population, we should say for all pickpockets or pickpocket offenses in this area, So now that we have the parameter in, we just mention the values one more time, is between 405.08 and 621.56 dollars. I don't know why I went that route. Putting the dollar sign in would have saved a little bit of writing, but this is just another way to say the same thing. So that does it, folks. That's confidence interval for a population's mean now. Any less questions at all, putting this all together? Okay, notice this part using the context. It's completely automatic if you've already used the context once already in their part A. And if we made a mistake in part A writing this down, but we carried it over, you're not going to get double jeopardy on this. So whatever you said your parameter was, if you fit it back in and mention the confidence and the bounds, you would still get full credit on this last part E. But that's the conclusion. This is how this all works. Tricky parts are nailing down the parameter, getting the critical number T star just right each time. We'll practice a couple more just to get the feel for how these go. Any last questions or comments at all before we try out a brand new one? Okay, so here's the new one for the day. These are data that we looked at before. It's kind of scary data in a way. It's about the early onset of dementia. This is from Alzheimer's Care Quarterly, so very, very serious data. Starts off with general context. This seems to be all about onset of dementia, but they tell us a little bit more. Well, no, this is just an Alzheimer's Care Quarterly. It's not all about Alzheimer's. They tell us dementia is the loss of intellectual and social abilities, severe enough to affect judgment, behavior, daily functioning. People with dementia sometimes are extremely impulsive, possibly quite gullible, possibly angry people. All sorts of things are going on. And Alzheimer's is the most common form of dementia, they tell us. In the article, Living with Early Onset of Dementia, so now we're talking about something entirely kind of new, a little bit more scary. The authors P. Harris, J. Keaty explored the experiences and struggles of people diagnosed with dementia and their families. So it tells us, well, this is what they did. It was a pretty big study. They're discussing the people with the condition. They're talking with the families of the people with the condition. But what is the data we're actually studying? Starts right here. Simple random sample of 21 people with early onset of dementia. So a sample size of 21. This is also going to indicate our population. When it says 21 people with early onset of dementia, that means our population is going to be all people with early onset of dementia. Again, we can be picky on this. Maybe we should say all people diagnosed with early onset of dementia because everybody in our sample has been given that diagnosis. So that's the samples, 21 people. The actual data is right here, but the data itself is age at diagnosis in years. Again, it's kind of scary data. I mean, 60s for early onset of dementia is rough because that's not even close to the retirement age. You've got like practically a decade to go if you're 60, and probably even longer after 10 years goes by, who knows? And some of these people are in their mid to low 40s, really scary looking data. So it's something we want to study. If we look into the population of everybody diagnosed with early onset of dementia, what is the average age of diagnosis? We can find that out if we look into the statistics of these data from the random sample. So this problem goes a little bit differently. Notice we don't have Y bar whatsoever, and we don't have S. So that's where we should start. We need to summarize these data with these descriptive statistics. It did not. But you know what? We could probably figure this out pretty quickly. Let's take a look into that. I'm kind of curious now. I've noticed that a lot of my data is usually at least or at, yeah, about 15 years old for the most recent stuff.
That's pretty scary because that list that you showed, most of the people were a lot younger than others.
Yeah, so this is a nasty condition. I'm in that range as well. So let me see. Age of study. Well, if you trust AI tools, here's a quick answer to that. Oh, looks like this is a problem out of a textbook for sure. Hmm. Looks like it was a 2015 study based off the source that's getting pulled up. No, that's a film. Hang on. Not too sure how to use these links here. We'll have to look into that later. I'm not getting a good result here. Maybe it's this. Sometimes it's kind of interesting to go to the actual study when you can. If it was this study, I'm not completely sure. Checking the authors. Authors were Harris Keedy, and I don't see those authors.
I would copy and paste what you copied and pasted in person, Alzheimer Care Quarterly. Copy and paste that into, Google Scholar.
Let me give that a try. So Google Scholar. I don't go there very often. And this whole
Yeah,
thing
the
maybe
whole thing, the volume 5, issue 2.
is doing more serious research at this point.
Still a Google search,
With hopefully less fluff.
no dice.
I'm not seeing those authors. They were supposed to be, let's see, Harris and Keedy. Let's add that. Here it is. Hopefully that's related articles. How do you get into that? Well, we can cite it, and that's giving us finally an answer to the question. This looks like 21-year-old data roughly. Yeah, that's hard to get the actual study on this. It's kind of amazing. Gonna have to contact some libraries to actually read this thing. It's not even on Google from what we can find. But looks like 2004 is the answer to that question. That was a good idea with Google Scholar. We're learning all sorts of interesting things in this class. Other questions about the data so far? Okay, well, next thing we need to do is crank out these statistics. And this takes us all the way back to chapter 2. The reminder on that one is you want to hit stat and then enter right away to begin entering the data. Because we've been in chapter 7, you probably have a L2 column. There's no harm in leaving it there, but it's going to distract me. It might make me put in data wrong. So I'm going to clear out L2 as well as L1 to start this out. There's 21 observations, which is a little bit on the high end. I'll never give you a final exam that has, say, more than 30 observations. That'd be too much for one exam. So I'll go column wise and get quiet as we data enter. Okay, I think I've got my data. And we need any additional time? Okay, with that data in, again, this takes us back to chapter 2. Life seemed a little simpler in this class way back in the day. But the thing we hit next after putting in the data is the stat key, right arrow over to the calculate button, and just hit enter a bunch of times. Maybe first verify you see L1 here, but it shouldn't be changed from what you were doing earlier on. And then there's a big warning about this. Recall X bar is Y bar. My notes have been getting that mixed up here and there as well. Well, we have to know what to round this to. In view of what part B is asking and part C is asking, yeah, sorry, go ahead. Oh, I was over in, first when I was over here, hit the stat key again and right arrow over to calculate. So your screen should look like that. Then you should have a L1 here, and you're just pressing enter at this stage. Yeah, exactly. Absolutely. Thanks for asking about that. Other questions at the moment? Okay. So in view of what the parts down below are asking, let's round our statistics to 4 decimal places, just to be on the safe end. Y bar, which is the X bar, is 52.5238. This already tells us that the average age of the sample is about 52 years. We would say that that's our estimated average age for the population, that we need to know the standard deviation to get any notion of what the margin of error is on that estimate. So that's S coming in next. Here's where it gets tricky. Is it the 6.47 or the 6.31 value? Anyone see the correct value to use?
The X, right?
Yeah, good call. We always want to use SX right here. If you use sigma, sigma is saying that your sample 21 is not a sample at all. That's the population, and you took a census. This is the right value for the statistic, and the number is always a little bit bigger. So 6.4701. So standard deviation is pretty big on this. 6 years is a lot. In the terms of the 6 to 8 to 95, 99.7 rule, to get 95% of the population, that's a 13-year swing in one direction and the next. So the mean of 52 years is never the full story. Standard deviation is going to give us an idea of the margin of error. And we'll do even better by using the right thing, the right critical number T star. So now we're in the phase where we'll take a look into the underlying population, calculate the standard error, critical value T star. We're kind of low on time, so let's finalize getting the parameter down, and then we'll come back to the mechanics parts below when we do this on Wednesday. But let's see, what is that parameter? It's quantitative data, so we'll write out mu equals the population. We've mentioned a lot in class. You could say the population mean. That's the more official statistical way to say it. But it's just as good. It's a synonym to say the population average. Let's go with average on this problem just to convey that's an acceptable way to write it as well. It's kind of like in chapter 13 where you could say either proportion or percentage. But if you said percentage, you're actually doing a decimal swap. Here, there's no change in our actual numbers, just a different way to convey it. The population average, well, here we have to say what the data actually represents, what the quantitative variable represents. And then we'll say for all. And this part, we'd be talking about the population. So we won't write out the structure every single time, but if it's been helpful to you in chapter 13, this is a pretty good way to think about it. It's kind of like what we did in chapter 7 when we wrote out the slope. There's a real structure to how these things go together. So if you like to see it this way in your mind, it's a good way to connect the concepts. So anyone have any missing part, what the variable represents or the population?
Age at diagnosis years.
Absolutely. So age at diagnosis in years, just like you said, is what our quantitative variable, the average, the standard deviation, the data itself is representing. So age at diagnosis in years, then it's for all. And here we can be, again, pretty specific. It said the simple random sample of 21 people with early onset dementia, and there's talking about an age at diagnosis, which implies everyone in the sample had some formal diagnosis for having early onset dementia. I think that's pretty important in this problem. Knowing that the last problem with the pickpocket offenses were for all reported crimes, that was important too, but I think it was more subtle. In this situation, I think this would be a good thing to really mention because the difference between people having a formal diagnosis and the entire population with early onset dementia might be huge because this is now a healthcare issue. People with a formal diagnosis had the insurance to afford going to a doctor to have this done, and not everyone has that particular luxury necessarily. So I feel like this is a pretty big word this time. I'll say for all people diagnosed with early onset of dementia. Is there a big difference between the populations? Everybody with early onset of dementia and just the smaller population, those diagnosed, we don't know. That would be a huge unknown in this problem. But at least we know exactly what the population is that we're talking about in this one situation. On the next parts, we'll just calculate our standard error, our critical number. Using that, we have the confidence interval in a pretty short order. In some ways, chapter 14 problems are a little bit easier. In some ways, it's a little bit finickier, but it's all very similar to what we did in chapter 13. Well, any last questions at all, folks, before we call it a night here? Okay, any last additions or subtractions you make on the parameter? Sometimes people find stuff that I don't see whatsoever on these problems. Okay, well, have a great night, folks. We'll be finishing off example 4 and 5 when we return next class, and possibly looking into section 15.1 on the chapter 15 content. But have a great night, drive safe, and we'll be back at it next class. Yeah, it's going to be next Monday. Yeah, and it's going to be over chapters 7, 10, and 13. So our chapter 14 won't make it on.
Chapter 7, linear regression.
Yeah, exactly, it will. Well, we're going to spend the entire Thursday before going into the exam. So we'll spend our Thursday on taking questions from the 7, 10, 13. Oh, gotcha. Yeah. Yeah, we'll definitely have a review like before. And I still remember what you asked about the exam to review, that we'll definitely ask a question, even if I come up with one, and then we'll go from there. On the next exam, yeah. Just the 3, yeah. So our chapter 14 we're covering now is going beyond the exam 3 at this point. It could have fit on exam 3 possibly, but I felt like 2 conference interval procedures would be a lot for this one exam. Awesome, thanks. Hey, questions?
I'm just gonna turn this into,
Is this the conference interval one?
chapter, was 9?
Awesome, thanks.
Yep,
It's good to get them done early. That's when it's still fresh on your mind, right?
yeah, see. See what cracked into my lab, statistics, graph.
Awesome.
It doesn't affect your grade, right? Like, if I go in there and I can only get through like, say, 2 of the 5 questions,
No, that won't hurt you at
it
all.
doesn't matter, right?
No,
Until like the end,
that's right. Yeah.
like, if I just left them unfinished at the end of the class.
Yeah, at that point, so you'd get just the percent you got completed in that section. But even if you left it for a while and you came back to it, say on finals week and finish it off, you'd bring your score right back up. There's no penalties on late dates and stuff like that.
Okay. Cool, yeah, have a good night.
You too, take care.